Okay, so I'm going to briefly review Standard 5B, which is corresponding to Section 6.2 in the HMH book that we were using. Remember, you can access that online if you don't have the physical copy at your house. This is no substitute for actually studying the material, since I'm just going to kind of give a brief overview and kind of talk about some of the subject headings and some of the main ideas. So I'm going to start just by going over the slide of very, very brief overview that I prepared for you here. So the standard itself reads, I can explain how balancing and reinforcing feedback loops impact Earth's energy budget, the greenhouse effect, and climate change. So big things there are the feedback loops, Earth's energy budget, greenhouse effect, which connects to Earth's energy budget, and climate change, which is the idea that man-made causes are increasing the average global temperature. So the Earth's energy budget is what tracks all the energy input and output within the Earth. So input is energy coming in, that would be from the sun. And then output would be energy leaving the Earth in the form of infrared radiation. But in the process, not all energy leaves directly. Some of it's absorbed by other things or reflected and whatnot. So that's what Earth's energy budget discusses. The greenhouse effect, it relates to that, is when infrared radiation comes up from the Earth. That's after the Earth absorbs the solar radiation. And then infrared radiation is absorbed by greenhouse gases and then re-emitted randomly. And so that could be back down to the ground, that could be into the atmosphere, that could be out into space. But either way, because of the atmosphere and to the ground portions, it's going to trap some heat, essentially, which keeps the Earth warm. A feedback loop is when a stimulus either creates an effect that reinforces or counteracts that stimulus. So reinforcing would be reinforcing feedback, otherwise known as positive feedback. I'm like catching typos as I read this to you, which is the idea that something happens and then a cause and effect chain occurs that then makes the original effect even stronger. So for example, the rising temperatures of the Earth cause more snow to melt, which means the albedo is decreasing and more sunlight's being absorbed, warming the Earth even more, and therefore more snow would be melting. Negative feedback's the opposite, is when it counteracts or balances itself. So for example, rising temperatures might cause more water to evaporate. That means there are going to be more water in the air and more clouds. Clouds have a high albedo, reflecting sunlight and therefore lowering the Earth's temperature because less energy is being absorbed. And then climate change is the idea that Earth's long-term weather patterns are changing. Some climate change is natural, but scientists believe that it occurs over a very, very long time, not like what we've been seeing now, which we've seen temperature changes in decades or centuries, which sounds like a long time still, but compared to these other natural processes, it's really not. Okay, so now I'm going to flip through the section 6.2 and go over in a little bit more detail. Okay, here we go. So one of the phenomenon that this section kept coming back to was drought. So that's a picture of drought. We're considering Earth as a system. It's closed, which means matter doesn't come in, but energy can come in and leave. We talked about cycling of matter in this section as well, specifically with the context of carbon dioxide, because carbon dioxide is a natural occurring chemical. It can come from cellular respiration, right? So whenever we breathe, we are exhaling more carbon dioxide than we breathed in. However, combustion, like we spoke about with the last section, is the original energy source that humans have used. And so because we're relying on combustion, we're putting in a lot of carbon dioxide. Now, some of that carbon dioxide might go into the ocean or might be absorbed by plants, but most of it's just kind of hanging around. And since it's a greenhouse gas, it contributes to climate change. This section is going to start getting into Earth's energy budget or leading to it. So it talks about how the energy is coming from the sun. Because of the tilt of the Earth and whatnot, you get seasons because different amounts of energy are coming in because days are longer when it's tilted towards the sun, which would be summer for us. We also talked about how energy can move around through convection currents, which actually is going to come back in Unit 6, which we'll start. Well, we'll talk about convection currents next week, on next Monday. But the idea is that when it's hot, the air rises, and so it takes that energy with it into the atmosphere and eventually creates this kind of cycle moving the heat around. You also have convection currents in the ocean, which the wind drives. So, for example, we're right here on the west coast of America, and so because our water is coming down from the North Pole, the water on our beaches tends to be a lot colder than, let's say, if you're on the East Coast or like the Gulf of Mexico, where water is coming up from the equator. So the greenhouse effect, this is key. This is one of the most important parts of this standard, is the idea, as depicted in this diagram, that sunlight comes in, is absorbed. Some of it's reflected, but most gets absorbed by either the atmosphere or the Earth. And then any time something has heat, it emits radiation because of something called the second law of thermodynamics, which again, we'll talk about later. A hot substance, emits infrared radiation, which is invisible to our eyes because it's too low energy. And that infrared radiation goes straight out. A lot of it can just go straight into space. Some of it gets absorbed by greenhouse gases, and like it says here, re-emitted infrared radiation, and that might go into the atmosphere or it might come right back down to the Earth. And when it does come back to the Earth, that's going to keep the Earth warmer. So without the greenhouse effect, we would die. So I don't want you thinking, oh, the greenhouse effect is bad. It's just too much of a good thing, can change climates, and that can be a problem, right? And again, carbon dioxide is a greenhouse gas, and we burn carbon dioxide. Or, well, we burn things and it produces carbon dioxide, sorry. Okay, so you see a lot of figures like this when it's talking about Earth's energy budget. We can actually quantify how much is reflected versus absorbed and whatnot, or reflected, right? So here, the incoming solar radiation, 22 is reflected by the atmosphere, 7 by the land, and so that leaves 23 and 48 that get absorbed. And so in the end, 71% is also being emitted because everything that comes in has to come out if the Earth's energy budget is balanced. And if it's balanced, then the temperature won't change. And so currently, less than 71% is going out, if you want to think of it that way, because the Earth's energy budget is not balanced. The temperature of the Earth is changing on average, although just a little bit each year. Okay. So scientists use satellites to make a lot of these measurements, so they're getting more and more accurate. Earth's energy budget, climate change, there's a lot of different factors. There's a lot of natural ones, volcanoes, the Earth's orbit, the wobble of our axis, convection currents, all those things. We also focused a lot in this standard on ways that humans have impacted Earth's energy budget. So greenhouse gases, got to know those, but we also talked a lot about albedo. So here's an interesting picture where, because they're releasing all this soot from burning fossil fuels, the soot lands on snow. Well, soot is dark, and so it absorbs a lot more sunlight, has a low albedo, and that causes more warming, and it melts the snow. Okay. Another picture of this idea of Earth's energy budget. Here's one kind of zoomed in on the atmosphere. So that very first one that we spoke more about was kind of a brief overview. Here they're actually splitting into the different ways that heat rises into the atmosphere. Something that's kind of interesting is, we talk about infrared radiation, and it is important, but actually the biggest form of transport of energy into the atmosphere is actually evaporation. It's actually from water going into the atmosphere. And again, in this unit, we're going to talk about something called specific heat capacity, and we're going to learn that water is able to hold a lot of energy. And so for me, it's not really a surprise. Okay, we looked at weather patterns. We looked that there's a lot of variability One comment I made in class that I'll make again is sometimes when people look at this and there's a drought, they say, well, you know what, California just always has a drought. So it's not because of climate change, just natural cycles. And there's a little bit of truth to that, but the length and the severity of droughts have been getting worse, and the temperatures definitely have been going up on average, even though there is still a lot of kind of variability over the last century or so. So how do scientists get this data? So a lot of it is just measured using instruments, but some of the very, very far back data they get from tree rings. They can look at how fast the tree grows based off how far apart the tree rings are. Farther apart rings means faster growth. That means probably better weather conditions, more rain, and that kind of thing. They can also look at ice cores. There's not one pictured here, but basically what they do is they go to an area that's been frozen for a long time, like Antarctica or into the North Pole, and they drill a giant cylinder of ice. And they can look at little gas bubbles that get trapped in the ice, and they assume or conclude, I guess, that those gas bubbles represent the gas at the time of freezing. So they can figure out what the carbon dioxide or other gas concentrations were at that time in Earth's history. We can also look at more recent data about droughts. We see that there is some kind of cycling, right? Drought got worse, then it got a little better. Still, what I want to point out is the last 10 years have been drought conditions, which is, even though, we might get slightly more rain one year, we still have to worry about this issue of drought, and we shouldn't be exacerbating, making climate change worse when we have to worry about this drought. Okay, and we also looked at this idea of how warmer temperatures, even if there's rain, will still cause a problem for water management, which is really important in California. Because even if there is a lot of snow, if the snow melts too soon, we won't be able to save all of it. And so that's what this projected conditions is showing, is that the gap between the peak runoff, meaning when most of the snow is melting, and when people actually need it in the summer when it's hot, is far apart. And so that makes it harder to store it, and we have to release more of it to protect ourselves from flooding issues, which means we're going to have a shortage. Okay, let's talk about feedback systems. The greenhouse effect and feedback systems are probably the major parts of this standard I want you to focus on at kind of connecting both of those to climate change. So balancing feedback is the idea that it counteracts itself. So here's an example. CO2 concentration increases. That means higher temperatures, more evaporation, more cloud cover, higher albedo, less solar energy absorbed, and lower temperature. So it's counteracting itself. The higher concentration of CO2 is initially increasing temperatures, but then decreasing itself. Reforestation could also be not exactly a feedback, unless it's naturally occurring because of temperature change. So if you use this as an example, make sure to be careful. If we're talking about humans going out and planting a forest, I wouldn't necessarily consider that a feedback. Now, if we say that there's going to be parts of the Arctic that melt, and then more plants are able to grow, well, that's different, because now more plants are growing in a place that didn't really have them naturally. And so that's going to pull CO2 out of the air, decrease the greenhouse effect, and make it colder. That, I would say, is a balancing feedback that occurs naturally. The kind of artificial ones, I don't know that I would really consider it a feedback as much. You could make an argument. I just might not agree with you. Reinforcing feedback, or the idea of positive feedback, is when it kind of makes a cycle that makes itself stronger. So for example, greenhouse gas increases, global temperatures increase, that melts permafrost, which has greenhouse gases trapped in it. Those greenhouse gases are released, and therefore increase greenhouse gases even more. And so you can see how it kind of goes in a cycle. Drought is an example of a feedback system where when there's a lot of drought, it creates more dust. The dust goes on snow, and they use planes to kind of check it out. That decreases the albedo, makes it melt more, makes more drought conditions because it's melting too soon, more sand, more dust on the snow, and it reinforces itself. Okay, and that is it for this standard. I hope that was helpful. Feel free to drop by office hours with any questions.